Welcome to Complex Numbers Part 7, and this is the last one in the series here for this course on complex numbers. We will be seeing them popping up in a different area of the course later on. Have a look around the screen. I've got a question for you. Obviously, can you solve these equations? And if you watch the last presentation with de Moivre's theorem, you might have some idea. How many solutions or roots of these equations would you expect? Z to the fourth equals 1. Z to the fourth equals 2i. It's a degree 4 equation, isn't it? Highest power is 4. Would we expect 4 solutions? I don't know. So you might think about that. Here, can you think of two solutions to Z to the fourth equals 1? I guess, what? Plus or minus 1? Okay. And what are the other two? If it's got degree 4, we should have 4 solutions there, 4 factors. You might try to remember something about conjugates there. Okay, how does a complex solution or root hide in a real equation? Okay, over here, z cubed equals 8i. Oh, can you find the cube root of 8i? Would there be 3 of them? How does that happen? And z to the fourth equals -4. Hey, anybody in year 9 will tell you that's not possible because it's an even power. It's got to give a positive. What's your answer to that? Okay, well, we're going to find the answer to that. I hope you know the answer to that, actually, down here, straight up. And what sort of complex roots we would have. Would they be conjugate pairs? Is there an I in the equation? All these questions, so think about those. Okay, come down and let's see what we can do with solving these sorts of equations. Here you are. The sorts of equations we're going to be doing now are z to the n equals c, where c is some complex number, member of the imaginary number set. Okay, what would you try to do? Let's use the mathematics you've had already to see what you would try to do in solving this. I think there are 2 distinct ways you would think of it from the experience you've had with solving equations. Okay, do you have any idea? Okay, well, let's have a look at what I thought. Here you are. You could do the solution of the equation by inverse operations in reverse order. So z has been raised to the nth to get c. What would we do? Okay, I'll put a bar through there so it doesn't look like a 2. We would find the nth root of that side to get back to z, and the nth root of that, and this would come to z equals c to the 1 on n. Okay, that might be something that you could think of straight up. What's the other way that you've solved equations apart from reversing the steps there? It's a null factor law. What's that mean? Well, we'd like to take the equation and put all terms to the left so you get 0, heading off towards a null factor law. That's where that rule came from. Get all terms on one side and 0 on the rest, on the others, so that here we can then factorize this. How many factors? Z to the n factors. Okay, so we'd have n factors here, if you like, if we could break it down that way. And the null factor law says either this one must be 0, or this one, or this one. So if there's a product, etc. If there's a product equal to 0, the null factor law says one of the factors themselves must be null or nothing. You can't get a product equal to 0 unless you're multiplying by a 0. Remember that stuff. So, which way would you prefer to do it? And I guess what's most recent is de Moivre's theorem here to enable us to raise complex numbers to various powers, including, what did we say? Rational powers there. Okay, fractions, so roots, 1 on n's will do. The nth root of both sides, that would be, wouldn't it? Okay, well, let's do some and get excited. This is a very, very important thread running through this course. It's going to come up later where we see the nth root of a number as being very important, in particular the nth root of 1. Well, let's have a look anyway. Okay, come down and let's have a look at an example. Some screen clippings here from Hayes and Harris Publications, so you should have that book nearby so you can check it out. Find the fourth roots of 1 That was that z to the fourth equals 1 I had on the first page there, by factorisation and the nth roots method. Well, z to the fourth equals 1. Factorisation, all terms cross to the left. We know we're getting ready for a 0 here, getting ready for the null factor law. So z to the fourth take 1 is, what could we say? A little step maybe left out here. Z squared squared take 1 squared. Okay, so z squared plus 1, z squared take 1. Difference of 2 squares here. Okay, we've seen that before, difference of 2 squares, dots if you like. Okay, and then the easy one is this one, another difference of 2 squares. Z squared take 1 squared, z plus 1, z take 1, a plus b by a take b. And then this one we looked at before, the sum of 2 squares is also factorisable in complex number land. Z plus I by z take I, z squared take I squared, and I squared is -1, so it's z squared plus 1. Do you get it? Okay, so now putting each of those brackets or factors equal to 0 under the null factor law, we've got z equals plus or minus I and z equals plus or minus 1. Okay, so that's one method. Sometimes this may not be factorisable easily, and you haven't done any polynomials work yet. So let's say it was z to the fifth equals 1. Z to the fifth take 1 equals 0. Now, we'd say that z take 1 is a factor, because you know z equals 1 is a solution. But now, how would you get this other factor? Well, there is a little tricky way of doing it. I'll show you two ways, because at this stage you may not have done polynomials. So what do you need in here to multiply by to get z to the fifth? You need z to the fourth. Okay, and then you would generate a neg z to the fourth term there. So you would need to cancel out. There's no z to the fourth term up here. So you'd have plus z cubed, because that would give you the cancelling out z to the fourth term. That would generate neg z cubed, which doesn't occur up here either. So you want to have a plus z squared, so that would cancel out. And you can keep going, can't you? Okay, so then you're creating a neg z squared, so you want a plus z there. And you know the last one is going to be a value plus 1, so that times that is neg 1. So you would have those two, and then you'd have to put this equal to 0 or this equal to 0. So it does get messy once that gets past a quadratic in there. So you could do that method. You can do various division methods, which we'll see when we go to the polynomial section of this course. So anyway, think about that one. That's an interesting. Okay, now the nth roots method, which is more usual, so it's easier to get to higher powers with this method. Z to the fourth equals 1. We want to use de Moivre's theorem, raise both sides to the quarter to knock this out. So let's put 1 in cis form, because de Moivre is about cis, isn't it? Powers of complex numbers, best done in R cis theta form or polar form. Okay, so it's 1 cis, the size of the number is 1, so size cis of the angle is 0, but keep in mind we can go around 2 pi and be back there. And how many times do we want to do it? The degree is 4, so we really probably want to go around 3 more times. So 1 lot, 2 lot, or 3 lots to come back to this position. So our first starting value is cis 0, which is just 1. Okay, and then we're going to go around k, lots of a complete circle to get back to that point. So k, we should put here, where k is a member of the positive set of integers. Up here, k is a member of z plus, if you like. Okay, positive, well, it doesn't have to be, does it? Just z, it could be, you could go around the other way. Could go the other way, but we usually go positively here. So here, therefore, we're raising all of that to the quarter. Okay, and what is that now? Well, it would be k lots of 2 pi on 4. So this would cancel. So it's k lots of pi on 2. And you can keep going around. Here we are. 0 times 1, 2, 3, which is what we said. We want 4 solutions. And you're just checking out, why would you have 4 solutions? Because in your factors up here, with a degree 4, you had 4 factors. Okay, so that's the idea of the degree being linked to the number of factors equals the number of solutions, if you like, or roots of the equation. So we've got these here, and you can see now you've got I and neg I like you did before. And just reiterating something from before, z to the 4th, take 1 equals 0. How can complex answers like these hide and not be visible? You can't see any i's in there. Remember the rule there, or the Huttyism, is how do complex roots hide in a polynomial equation? Well, their sum and product must be, to make up a quadratic, sum and product must be real. And then they create a quadratic factor back up here. Here it is, back up here, a quadratic factor that hides the fact that they are complex roots there. So that doesn't show up in the coefficients of the equation. Keep in mind all of this. Isn't maths fun if you can think about why it's all happening? Because your year 9 student would say, well, okay, this has only got two solutions, plus or minus 1. And you know, of course, degree 4, how do you get up there? Well, the other solutions are complex. How do you get up to degree 4 with only 2 real solutions? So think about all that. Get up close and personal with maths. It's good fun if you do. Let's go down and have a look. And here's another little example, and then I'll let you loose on some. Find the cube roots of 8i. So solutions of z cubed equals 8i. Okay, so we're going to use de Moivre's theorem on this one. Okay, because z cubed take 8i. We're not going to try and factorise that. We're not going to try and factorise that idea there. Okay, so here, let's put 8i in polar form, so use de Moivre's theorem. So it's 8 cis now. I is pi on 2. So the size of the number is 8, so it's r cis pi on 2. Don't forget you can keep going around. How many times are you going to go around? You want a total of 3 solutions, so you go around twice more. So there's the first one, k equals 0. Then we'll go around k equals 1 lot of 2 pi. Then we'll go around k equals 2 and generate our 3 solutions. What would happen, questioning here, if you went around another time, k equals 3? Should we look at that? We might look at that in a minute. Okay, so here you are. You're going to raise it to the 1/3. And it would be good to put de Moivre in there, because that's how come you can raise that to the 3rd and divide the argument by 3. That's de Moivre's theorem. Okay, so you could here work with pi on 6 there, and away you go. Here what they've actually done is to say, well, that pi on 2 is going into the bottom line as a 6, and multiplying that by 4 pi. So you can do that, or you can just add on 2 pi on 3 there. So pi on 2 is plus 2 pi on 3. Either way, so the number out the front is going to become 2, and then you're going to get pi on 6, and then one more lot of it, of 4 pi on 6, or 2 pi on 3, and another. So keeping it in pi on 6s isn't a bad idea. Okay, so just notice this step here. The 2 went down the bottom, so it's pi, plus, but if it goes down the bottom, this has got to be 4 pi, so that when you divide it by that extra 2, it comes back to 2 pi. So just watch that now. So we've got that. Now what would happen if we put on another one? If we went around again to k equals 3. So what would we be adding on? Well, we're adding on another lot of 4 pi on 6. So it would be, what would it be? 13 pi on 6 in here. 2 cis 13 pi on 6, which is 2 and 1 6 pi. You're back around to the original number. So they start to repeat themselves there. There's only 3 distinct roots of a cubic, okay? And so if we're finding the cube roots, it was in 8i form, at the beginning, that's Cartesian form, so we've got to put this back. The rule is to put each of them back into Cartesian form at the end, and we get 3 roots of that equation. Quite clearly they're not occurring as conjugate pairs. They don't, they appear in the equation, don't they? Z cubed equals 8i, or Z cubed take 8i equals 0. That I is obviously showing that there are some complex roots. And that's because these cannot hide themselves. They're all complex and not in conjugate pairs there, sorry about that. And so they are going to appear in the coefficients of the equation. It's not a real equation. It's got complex coefficients there, or constant. All right, are you getting the idea? Here we are, and we could plot those solutions. Just notice they seem to be uniformly distributed around the Argand diagram there. Why would that be the case? What's the separation there? How did we generate them? Okay, by adding on how much? Okay, I think it's about a third, isn't it? A third of a revolution. Every time we went around 2 pi by De Moivre, we had to divide by 3. So can you see what this sort of operation now with the cube roots of something are going to give you equal spacings here? Because each one is generated by revolving around another 2 pi, and De Moivre's going to come along and find a third of that. So can you see this looked interesting with the equal spacings of the solutions around the Argand diagram, but as a budding young mathematician you can see why that's always going to happen in this scenario, in this situation. All right, come down and practice some and it'll be a little bit more obvious then. Okay, here we are. Find the 3 cube roots of 1 using both methods and so on. I think you should be able to do these. You need to do all of them because this is a very important thread in the course. It's coming up later in something called quadratic iterations. We're going to see this again. And it's a very important notion. Okay, I'll pause the presentation, have a go, and I'll show you the fully worked solutions down below in a minute. So here we go. Check this out now, question 1, A and B. Don't worry about this. This is the book's way of showing you a polynomial division, which we'll do when we come to polynomials. And have a look at that. I would have liked you to try to generate that factor by the method I was using before, by sussing out what terms need to be generated to get the original cubic here. Okay. Anyway, talk to your teacher and other students about that one. We'll leave this, just get rid of this. We'll leave, hang on, sorry about that. We'll leave this to polynomials. All right, come down now. Question 2, there's A and B, so check through, very, very important idea there, with this step particularly, where you're finding a third there. Okay, come down now and let's have a look at question 3 and 4. Okay, can you explain why the solutions are equally spaced around the Argand diagram? And what is the separation of those? What is the changing argument here? And why does that happen? Particularly answer that, I think. And here, if you were to draw them, would they be equally spaced? And what would that spacing be from the mathematics here? From that quarter, what would the spacing be? Okay, let's go down here and have a look. Question 5, same thing. Again, I asked the question. They look to have equal spacing. You could guess the change in argument here, I think. I think you could guess that. Why is it happening from over here, from these 2 lines here? Why is that happening? All right, okay, let's go on and have a look particularly at something that's coming up later, and that's the 4th roots of numbers, in particular later on, the 4th roots of unity of 1. Find the 4th roots of neg form. 4 in the form a plus bi, and then factorise z to the 4th plus 4 into linear factors. Hence why z to the 4th plus 4 is a product of real quadratic factors. Well, that's interesting. We know that. That is coming back to the reverse of the method of factorisation to solve the equation. We'll find the roots and reconstruct the equation afterwards. So let's change neg 4 to r cis theta form, so it's 4 cis pi plus 2k pi. Okay, so then we're going to use De Moivre's theorem here, and when we do it, De Moivre there, we're going to raise everything to the quarter, so it's 4 to the 1/4, and finding a quarter of this, pi plus k times 2 pi on 4. Okay, so if you like, it's they've left this little step out here showing you how to get from there to there, but it's going to be pi on 4 plus k lots of 2 pi on 4, which is pi on 2. So you're going to be adding pi on 2's every time. A pi on 2 is a 2 pi on 4, so this goes from pi on 4 to 3 pi on 4, and then to 5 pi on 4, and then 7 pi on 4. It's easy to see why, because the 2 pi, to get back to the same position around the Argand diagram, is being divided by 4. So that's a pi on 2 separation each time. And so guess what the solutions are going to look like down here? They're going to have a pi on 2 separation, aren't they? Are you getting the idea of why that works? I hope so. So now we've got to do a step where you need to remember the sine and cosine of pi on 4, the working angle here. So there's the first one, sine pi on 4 plus cos pi on 4i, and 3 pi on 4, second quadrant, remember this stuff? So the cos is going to go negative, the sine's still the same, and then the next quadrant, they're both negative. Remember this in the work on the unit circle. As we come around to 5 pi on 4, we create congruent triangles, that's pi on 4, and that working angle in there is pi on 4, but both cos and sine are negative in this quadrant, negative. So you've got cos pi on 4, 5 pi on 4 plus I sine pi on 4, both are negative. Then in the final quadrant, cos goes positive and sine stays negative. So we can go back to Cartesian form, and I didn't look at this, did I? 4 to the 1/4 is 2 to the 1/2, if you like, and root 2 is the answer to that. So that goes out the front, and we've got some cancelling here when you multiply that out. So we've got 1 plus I, neg 1 plus I, neg 1 take I, 1 take I. And here they're bringing up that point, conjugate pairs. Hey, all these values of this fourth roots of neg 4 were all complex. Yet in the equation, z to the 4th plus 4 equals 0, there are no complex coefficients. It's a real equation. How did they hide? Here it is down the bottom here. How were they hiding in there and they couldn't see it? Their sum and product of both pairs being conjugates is real. So it hid in there. Okay, so z to the 4th plus 4, let's look at the quadratic factor, which hides the two roots 1 plus I and 1 take I. They have a sum of 2 and a product of 2. So it's z squared minus the sum of the roots plus the product of the roots to get that equation, or that factor giving rise to those roots. And the other ones, this one here, neg 1 have a sum equal to neg 2 and a product equal to 2. So there is minus the sum of the roots in front of z plus the product of the roots. So overall, you have two real factors, both hiding a pair of conjugate roots there. Okay, magic mathematics, isn't it? Fantastic stuff. All right, come down and I want you to do some now. So here we are in question 6. Find the 4 solutions of that and giving each of them the form and display them on an Argand diagram. And I want you to predict while you're doing the work, as you go through that De Moivre step, predict, are they going to have equal separation and what would that separation be? Okay, don't forget to write as a product of two real quadratic factors. Okay, so this we'll have two real quadratic factors, but I bet you there's a few i's in there. Hey, all right, have a go. I'll show you the answer now. Oh, the ship's on the tilt here, I think. Must be going through rough weather. All right, so here we are. How did you go? Did you spot that it's going to be 4 lots of 90 separating it before you drew that? And here's the step up here. A quarter of 2 pi is pi on 2. So you're going to actually pop pi on 2 on every time now, because you're going around 2 pi, and then de Moivre's coming along and finding a quarter of that. So the angle there's going to be pi on 2, equal spacing of 90 degrees there. Okay, wonderful mathematics. Okay, have a look down here at the sum and product of the roots there, and again they occur in conjugate pairs, giving rise to a real quadratic factor. Okay, let's keep going. A little bit left to do with the roots of unity, and this is very, very important later on. We see this come up in a section called quadratic iterations. Okay, the nth roots of unity are the solutions of z to the n equals 1. Fair enough, and we've said you can solve this using factorisation, probably not past degree 3 because it's hard to do. So we'll go to de Moivre's theorem, z to the n equals 1. We'll raise both sides to the 1 on n, or the nth root, that's why it's called that. And so z is going to be equal to 1 to the 1 on n. And there are going to be n solutions. We'll generate these, won't we, using cis form, realising there are some complex roots in there. Okay, let's have a look and see another example here, and we'll work through that. Find the 3 cube roots of unity, display them on an Argand diagram. If omega is a root with the smallest positive argument, that's your starting one, show the roots are connected by this relationship. And this is very, very important. Let's have a look. Solutions of z cubed equals 1. So write 1 in r cis theta form. It's 0 plus k times 2 pi. There's 0, cis 0 there, 1 cis 0. So therefore, we can say z cubed is not just equal to 1, it's equal to cis k times 2 pi, where k is 0, 1, 2, 3, 4. Whatever we need, we only need 1 and 2. Okay, for 3 roots. So here it is, de Moivre to the rescue, de Moivre's theorem. So z equals cis k 2 pi on 3. So k is 0. We got the first one, cis of 0, which is 1. Add a 2 pi on 3. Add another 2 pi on 3. So we're going to have separation here, aren't we, between the roots of pi on 3. So come over here, pi on 3. Here, pi on 3. Hang on, I must make 2 pi on 3. 2 pi on 3. 2 pi on 3 here, because that's what we're adding on. We're adding on 2 pi on 3 each time. Okay, so letting k be 0, 1, 2. We'll just set up here anyway. All right, so now bringing them back, because 1 is really in Cartesian form given to us, we should state our answers in Cartesian form. So we have to do the cos plus I sine of 2 pi on 3. And here it is written here, and here working angle is pi on 3. So cos of pi on 3 is a half, and sine of pi on 3 is root 3 on 2. So that's our working angle, and then we've just got to adjust the positives and negatives of the two depending on the quadrant. Okay, so now this is an interesting result here. Show up the top, show that 1 plus omega squared is 0. So if omega is the solution with the smallest argument, there it is there, that's the one there, so we've got 0. And then how do you get from that one to that one? Well, you could think of it adding 2 pi on 3. That's what I did to get the equal spacing idea, get a reason for that. But you can say by de Moivre, then we should put this in here, de Moivre's theorem. De Moivre's theorem. When you square this, it becomes cis 2 pi on 3 all squared, which by de Moivre's theorem, you multiply the argument by 2. Okay, so you must spell this out here. This is a very common question, to show that the roots are 1 omega and omega squared, where omega is the smallest one, and you're explaining ways of going to the next one, aren't you? There's the smallest one, 2 pi and 3. This is 4 pi and 3. You've added 2 pi and 3 because of this working bit here. The spacing is 2 pi and 3. But also, it is squared under de Moivre's theorem. You could think of 2 pi and 3 being squared to 4 pi on 3, or cis 2 pi and 3 all squared to go to cis 4 pi and 3. Okay, so please spell that out. The idea here that the smallest one, when squared, will give the next one there for that situation. Okay, and now we want to show that this comes to 0, so 1 plus omega, or you're adding complex numbers, we will use Cartesian form for that. And you can see how they cancel out, all the pieces cancel out here. Okay, and come to 0. All right, so that's an interesting result. And I suppose you might ask, well, could I have shown this vectorially? Because they can all be represented on the Argand diagram. Could you have shown that vectorially? Well, I think you could have. We might do that in a minute. Come down now. 2G2. Here we are. Quite a few to do here. Here's the answer to that one there. Can you show by vector addition that the 1 plus omega squared equals 0 if they are the cube roots of unities? That's the one I was just talking about. So go back up and get those vectors and see if you believe they do give a closed figure. The sum there would be 0 if they form a closed figure, those vectors. All right, have a go. Question 1 through 4 there. See what you think. Okay, and then 5. All right, I'll show you the solutions now. So come down. Need to work through these with classmates and a teacher. The ship's rocking a bit here, going down and down over waves by the looks of things. Okay, so come down here to part 3, the rest of part 3. Be careful there, that's interesting. Okay, and then question 2 and 3. Whenever you get this equal spacing, do you know why it occurs? Can you show the sum around a closed figure? Okay, and let's go down to question 4. I'll try and get all of question 4 on there. Oops. Well, A, B and C. Are these equally spaced and why? Okay. Vector addition here to show that it's 0. Okay. And question 5, A and B. All right. Did you have fun? We're going to pick up on some stuff with complex numbers in a later section. So try and get your head around that. I hope to catch you then. Cheers for now.